Okay, page 7 now, question 16. We're looking at an alpha particle. It is approaching a nucleus and then shooting off in this direction. And again, we're looking for a single correct statement. And of course, 3 of these have to be wrong. The first one we're looking at is its acceleration is 0 at P. P is the closest point to the nucleus, the point of closest approach. Well, actually, when we get closer and closer, when we get to this point P, we're the smallest distance that we can possibly be from the nucleus, which must mean that the force is going to be the biggest. And seeing as we know from Newton that F equals ma, so A is F over m, the larger the force is going to be, the larger the acceleration is going to be. So the point P is actually going to be the point where we are accelerating the most. The acceleration is certainly not 0 at P, otherwise we would see it moving in a straight line, and it's certainly not doing that. For the statement B, its kinetic energy is greatest at P. That is obviously going to have to be wrong as well. This thing is slowing down as it approaches the nucleus. The nucleus is positive and so is the alpha particle, so they're going to be trying to repel each other. So as this comes closer and closer, it will slow down because the nucleus is trying to push it away. Now you could think about this in another way. You could think, well, what's happening to the potential energy of this alpha particle here as it approaches the nucleus? They're both positive, so it must be increasing in potential energy as it's going there. The only way it's going to be increasing its potential energy is if it's decreasing by the same amount in its kinetic energy. So its kinetic energy is actually going to be decreasing and decreasing and decreasing. It's actually going to be least at P. So these two statements are completely false. Statement C, its speed is least at P. Well, that's actually going to be true, because as we get closer and closer to P, we're going to be increasing our potential. Our potential is going to be a maximum at P. Potential energy is maximum at P. That, as we said, is coming from the kinetic energy, so the kinetic energy must be minimum at P, so its speed must be least at P. So statement C must be correct, 16 must be C. And just to complete this, 16D, its potential energy is least at P. Well, we've already discussed that, haven't we? We've said that the potential energy increases as we move closer and closer to the nucleus. Question 17 then, we have two capacitors. We have a 1000 microfarad and we have a 10 microfarad capacitor, and it says specifically they store the same energy. So we're going to be thinking first of all about the equation for energy, and it's going to be the same for each. And we're going to work out what the voltages are across them. So my first capacitor has a capacitance of 1000 microfarads, which is going to be 1000, of course, times 10 to the minus 6 farads. That's going to be C1, if you like. There's C1. And C2 is going to be 10 microfarads, so 10 times 10 to the minus 6 farads. There's C2. Don't really need to draw it, but there it is. And across there, I suppose we could draw this across here is going to be V1, the voltage across there, and this one across C2, the voltage is going to be V2. We want to know what the ratio of V1 over V2 all squared is going to be. So let's consider these energies, because the thing that the information they give us is that they're storing the same energy, and we know that the energy of a capacitor, well, we can give it in a number of different forms, but seeing as we've got the capacitance and the voltage, let's go with that. E is going to be half CV squared. So I can confidently state that the energy across here, we can describe that as half C1 V1 squared, and that has got to be entirely equal to the energy across this one, which is going to be half C2. Oops, C2 V2 squared. So those two things are going to be exactly the same. Well, these halves obviously are going to cancel. That makes things nice and easy. And we're trying to work out what the ratio of V1 over V2 all squared is. So let's just divide both sides by V2, because then we'll have a V1 squared over V2 squared. So we're going to end up with C1 V1 squared over V2 squared, and that's going to have to be C2. Divide both sides by C1 and we'll have our answer, V1 squared over V2 squared, which of course incidentally is just V1 over V2 all squared. So that's going to be C2 divided by C1. Well, we know what the capacitance, so C2 over C1 rather, we know what the capacitances of these two are. We know that's C2, that's C1, so we can just substitute those values in. C2 is going to be 10 times 10 to the minus 6, C1 is going to be 1000 times 10 to the minus 6, so it's the same as doing 10 divided by 1000, it's going to be 1/100th. So the answer to question 17 is going to be B.